channel. My name is Opubo. For those of you new to this channel, welcome. And for those returning, I bid you welcome back. Good to have you return. You are well appreciated. As always, in this channel, I present various ideas and designs of technologies, mostly from the Technology IP Bank of Enhanced Knowledge LLC, often integrated from several other technologies and made ready for adoption by the Adoption Brokerage Division. This presentation focuses on conservation economy, NormTemp air gas process technologies, which focuses on the provisioning of the components of air gas, nitrogen, oxygen, and carbon dioxide in as large quantities as required at normal temperature, abbreviated as NormTemp, as foundational needs for enabling a conservation economy from the technological perspective, and the approaches citizens of a geographical space, community, region, or even a nation could adopt towards deploying the technology to ensure the sustaining of a conservation economy. Of course, this is one of the technologies defined as essential technologies for a conservation economy, with the basis of essential, though defined in the contextual characteristics, are yet modified somewhat by derivative essential needs as defined consequent on the prevailing civilizations and the underlying science. Digressing, however, for a moment before making a deep dive into the air gas processing designs. If you have not as yet subscribed to the channel by simply clicking on the subscribe button below, I implore you to do so. Please click the subscribe button now. The subscription would cause the system to keep you informed by notification of the next presentation the moment one is published, and also, of course, help me to more consistently continue to imbue you with the peace dividend of conservation economy. Now, back to the presentation. Science underpinning the prevailing civilization. Existence of life is supported on the availability of air gas, nitrogen, oxygen, and carbon dioxide, with different kingdoms of life dependent on each type of the air gas. Humans, animals, and plants dependent on oxygen, algae, bacteria, blend nitrogen fixing, dependent on nitrogen, and algae and other microorganisms dependent on carbon dioxide, and as was also identified in the context elicitation via the need of algae for carbon dioxide. The manner of availing life, whether unicellular, multicellular, or complex cellular with air gas, has been mixed. When large volumes of each type of air gas is needed, often energy is expended to cool the air gas to temperatures low enough for the needed air gas to separate out by liquefaction. Of course, this approach is energy intensive, entailing consumption of huge amounts of energy, and also requires devices and equipment affecting some extreme conditions, and as such imposes restrictive implementation. The technology of significance then must necessarily accomplish the same at room temperature, or otherwise normal temperature, abbreviated here as NormTemp. A technology integrated out of the technologies of the Technology IP Bank, premised on a rather obscure science, is air gas process technologies, which is a two-technology combo consisting of a product technology and a process technology that manufactures the base product adopted in the offered product or product technology of the air gas separation process. The base product, essentially a complex structure of sorts, is permeable by production conditions to enable the separation of the air gas at normal temperature, abbreviated as NormTemp, and therefore avoid the requirement of liquefaction and correspondingly the immense cost of cooling. The manufacture and production of the base product, however, is performed with a special chemical process technology, air gas chemical technology, the concept design of the process technology being as shown in the figure. Actually, the chemical technology utilizes a chemical raw material in an environment that causes the material to form permeable complex structure, gas-specific sizes, as set at production runs. The complex structure is then deployed in a design that permits just the target gas out of a mixture to preferentially diffuse through. The air-gas separation process is simply a preferred form of the deployment of the base product as shown in the product. Yet, at deployment, at the point of use may be of designs of any geometric form deemed applicable for the adoption needs. Design as per the image, the chemical technology consists of two storage tanks, a dissolution reactor, a particulate crystallization reactor, and a structure cementer reactor. During operation, one of the two-stage reactors is charged with powder of chemical substances, and the other with a special chemical solvent. The solvent is fed into the dissolution reactor from the top, being sprayed into the reactor, and the powder substances are fed in entrainment from the bottom in bubbling upward flow and imploding on the liquid surface and discharging the rest of the powder particulates on the surface to be fully wetted from the aspirations of the liquid. The bubbling process causes much of the powder to become wetted at the bubble meniscus and accordingly dislodge from the tumbling flow of the bubbles into the liquid, and of course falls through the solvent by gravity and dissolves during the gravitational downward pull, but ultimately dissolving virtually completely before reaching the bottom. And the mixture then flows out through the outlet for the liquid at the top and is pumped into the crystallization reactor bottom upwards. In the crystallization reactor, new particulates then form and of sizes subject to the set operating conditions, but entrained upwards yet, being that the hydrodynamic drag forces of the convection velocity is large enough to still carry the particulates out. The effluent stream is then pumped into the cementer reactor, into which another chemical substance is fed. In this reactor, the particulates settle to the bottom by sedimentation, while the remnant fluid percolates through the pores in between. Meanwhile, the additional chemical in the solution then binds the particulates together into a complex solid structure of the particulates. As the height of the crystalline structure increases, the cementer chemical gets fully reacted and the remnant fluid becomes just residual solvent from the crystallization reactor and therefore is recycled back to a premixed tank before being fed yet again to the crystallization reactor. After the crystallization process grows up to a certain height, the feed into the cementer reactor is discontinued. The fluid is awaited to drain out and the structure taken out of the reactor by the bottom cap defixing and allowing until the structure is fully outside of the reactor body as shown in the picture right below the cementer reactor. And then it is removed for drying out in a low temperature oven that does not cause any annealing of the crystalline materials. And then there can be uniform acceptance that there is in fact a conservation economic technology that has the capacity to empower the extractive production from atmospheric air, any air gas, be it nitrogen, oxygen, or carbon dioxide, by separation at room temperature or at NormTemp, for use in every other conservation economy technology, including the biotics, resource, electric power technology. The materials of construction being mainly steel and of cylindrical forms, the technology is well suited for the utilization of used chemical process equipment, being pre-purposed for the operations of each type of reactor. The same is true of the storage tanks, which are also available in many numbers, contributing to the redeployment of the process equipment of shuttered chemical, biochemical, and water process plants. So under the requirements of conservation economy, this technology is just right in ensuring that process equipment that would otherwise be considered waste are utilized to the benefit of life. For forward guidance, the availability of the technology means that some pressing problems of humanity deemed to be a result of waste can now be addressed. For the recovery of the alleged waste and their utilization as raw materials for other needs of the conservation economy. One immediate such need for utilization of resources, otherwise deemed as a waste, are the large quantities of methane and carbon dioxide considered by some as the sources of global warming, or by euphemism, the cause of climate conditions. So, quite appropriately, the role of this technology in addressing the so-called climate conditions will be part of future sets of conservation economy technologies that would be presented. And if interested in licensing this technology, please send an email to me. The email address is put in the pinned link below as our other information. Regarding licensing consideration, there are some notes that should be of interest. Worthy of note that the design of the reactors, as with most chemical reactors, can be multiples, and each reactor can be of any multiple as required to only satisfy the production volume need and performance of each reactor. So there is no specification of the number of each type of the reactor that may be used in the production setting. Of particular note, though, is the dimensions of the particular cemental reactor. This reactor must necessarily be of varied dimensions because of the prospects of highly variable radial and height dimensional aspects as may be needed for adoption. And I thank you for being here, and I appreciate your coming to listen, and hope and expect that you would consider coming back for the rest of the presentations in the future. The fact is, even if you do not care to adopt the technologies, some might just change your perspectives of society and life. Until the next presentation, I wish you